Again, the point of this theorem is just to be able to get the expansion to this without having to FOIL 6 different times, because it's easy to miss a number or drop a term. I'm going to do it with 3 colors because I'm going to do 3 stages. I'm going to look at the x's first, then I'm going to switch colors and do the y's, then I'm going to come back and do the coefficients in a first color. I'm going to deal just with the x, and we know now from the pattern that x starts at n, decreases by 1 until you get to 0. First thing we have to figure out is how many terms does this thing have? How do we know that there are 7 terms? N plus 1. So right away, before we do anything else, we know how many terms the answer has to have. So I'm going to just set up blanks, and I'm going to space them out so I have lots of room. But I know I want 7 of these blanks because I need to fill in 7 different terms. I'm going to start with x. I know that x starts with the same as the exponent, so starts with 6, and decreases by 1. And I like to write the x to the 0, even though I know in a second it's 1 and I'm not going to really care about it. But just to fill in the pattern, I like to come all the way down to 0. And I'm going to switch colors now, and I'm going to do the y piece. And y is the opposite. It starts with 0 and goes all the way up to n. So I'm going to have y to the 0, y to the 1, y to the 2, etc. And we have a little built-in check at this point, because what do I know about the sum of these 2 exponents? Has to equal 6, which is the exponent. So just double check, do all those exponents in each term add up to give you 6? Okay, so it's like a little built-in check. After the first 2 steps, you have it correct. I'm going to switch to my third color, and what I'm going to do is put the combinations in. So I'm just putting the C first, and then we'll figure out what N and R are. The n is always the same as the exponent in the question, which is also the same as the very first exponent on x. It's always going to be identical. And n doesn't change for all of them. It's always going to be 6 as your n value. So 6, 6, 6, 6, 6, 6. The r always starts with 0 and goes up to n. So it's the same as the exponent on the y in the first term. And it always increases, so 1, 2, 3, 4, 5, 6. And then you can use plus signs in here. When we did combinations, which, that seems long now, I think it was last Tuesday, we looked at generally an NC0 and an NCN. It was one of the 2 patterns we looked at when we calculated that list at the beginning. And what did we say an NC0 was? Doesn't matter what it is, it's always going to be 1, because there's one way to pick no objects. And what do we say about an NCN? Also 1, because there's one way to pick all the objects. And then we talked about the pairs. The example we looked at was a 7C3 and a 7C4. And they both came out to be 35. Why was that? What was the pattern between 7C3 and 7C4? They have to add up. That's why Pascal's triangle is what we call symmetric. I'll flip so you don't have to. So remember way back when we looked at Pascal's, we said, it goes up and then it starts to go back down. It's because those 2 terms are the same. So for example, here we know a 5C2 is the same, or 5C1 is the same as 5C4. That's why they're the same. And a 5C2 is the same as 5C3. That's why you get this symmetricness in Pascal's triangle. Still with me? It's just the way they work. If the 2 R values add to give you N, they're the exact same number. Why this is important here is because I know this is 1 and I know this is 1, so I don't even need to bother calculating it. I know right away that an NC0 and an NC6 are, or a 66 are 1. I also don't care about the y to the 0 and I don't care about the x to the 0 because I know those are equal to 1. So it makes the first term and last term really easy because all I care about in this now is going to be an x to the 6. The second term is 6C1. Well, we didn't talk about it specifically, but within doing your combinations, you should have figured out what an NC1 is always equal to. What does an NC1 always equal? So if you have 6 objects, in how many ways can you pick one of them? 6 different ways. So this will always equal n. So without a calculator, we know now that a 6C1 is what? 6. So the second term is a 6. X to the 5y. The 6C2, you can use your calculator, or you can memorize Pascal's triangle and just get the last row of it. Completely up to you. I would probably grab my calc at this point, throw in a 6C2. Offer a 15. Colin's nodding his head, but he didn't even touch his calculator. Was that like a pity? That was like a pity confirmation. Did you already do it? Okay, good, high five. Did you hear about the job yet? No, you haven't heard, or no, you didn't get it? It's frustrating. Sorry, did we confirm it's 15? See, 62? And then I've got an x to the 4th and a y squared. 63. And he's followed by an x cubed y cubed. Now your calculator is useless to you. You don't need it to do the 6C5 or the 6C4. Why not? Because you know this is symmetric. So if it goes 1, 6, 15, 20, we're halfway in our terms. What does it have to be next? Back to 15, x squared y to the 4th, plus 6xy to the 5. And the very last term, I don't care about anything except that y to the 6th. We just expanded all of that without having to FOIL it 6 different times. That's the whole purpose of binomial theorem. A faster way to get this answer without having to multiply. Questions? Grab your phone, and you can either snap this QR code or go to that URL. I put a bit.ly at the bottom for you. Oh. It's like really close. It might be too close. I need to back up a little bit there. Has everyone snapped? Because I want to go to the website. This takes you to a website called Wolfram Alpha. Have you seen this website before? Okay. After we do this, I'll show you how beautiful this website is. But what this is a binomial expansion calculator. So for homework tonight, all I'm going to give you is 5 expansions I want you to try, and you're going to just check them using this. So all you need to do is punch in whatever the binomial is. So if we just check the last one we did, put x plus y. And then we had to the power of 6, so I'm going to put 6. Watch this. Bam, there's the answer. And all the computer's doing is exactly what we just did, just 1,000 bajillion times faster. So we're going to do one more example together, but then I'm going to give you just 5 expansions. You're going to do them the long way, then just check them with this that you have the right. Go to just Wolfram Alpha. So I don't know if you can click on the link like I did, or you can just type in. There's also an app you can download later, but this is kind of the main page. I'm just going to pause.